report on this computer. Thank you. That is a very good reminder. Let me just check, make sure we don't have anybody sitting there. Somebody's looking to get in. All right, we should have everybody, I hope. All right, so let's see what we got here. Well, at least this is going smoothly today. There it is. Okay, so, all right, I'm all set. So that the handout that we've got, right, that first day handbook for loads. And so that's where it also shows up. This is really what the activity will be about, the page 12 to 15. And then we also hit on this today a little bit later in that handout. So again, kind of keep that thing nice and close as you work through this. So all right, lateral systems in buildings. So we are going to focus now on looking a little more particularly at forces that come in the horizontal direction. And wind obviously gusts in the, it does gust in the horizontal direction. And then seismic forces, when we talk about forces, there's no actual force, it's actually the inertial, it's Newton's second law. So it's the inertial force. So it's the force of a body that wants to stay where it is. And so it's basically changing momentum. So we get a change in linear momentum. And so those are the forces that we deal with, and we put those then on the structure. And we'll look at both of these today, and only one of them is going to govern. And so in a design, I don't know why it does this. Let's see if we got this. So one of them will govern. One of them will be the design force. So generally, if we get a building, the taller or the wider, the bigger the face in the building, it's more wind driven. The smaller the building, it would also be more seismic driven. And we'll kind of see that today. We'll see that in our in-class activity. So when you select then both the system type and also that also relates to the material. And so then there's a very important factor, this R factor. And so that R factor is what adjusts for, it's called the seismic response modification factor. And it modifies, it gives you a reduction in the seismic force if you have a system that is ductile. And so what that means is that we look on, and you've kind of seen that on some of the content earlier, but on one end of the spectrum, it would be something that's very brittle. So this would be like glass. Concrete is also very brittle, actually. It's a response that occurs very quickly with very little notice, like a shattering of sorts. A ductile response would be one that can go far into the inelastic range. So from a building perspective and from a design perspective, when we think of life safety, materials that are more, and systems that are more ductile are more life friendly in a way. So you're going to calculate the lateral loads. That's a little bit more back on class 5. I'm going to just give you a quick overview. So you'll end up dusting that off today when we do our in-class activity. Configure lateral system and layout. We're going to talk about that today. That won't be what you do on your in-class activity. And then we also begin the element design. And so, right, wind, we calculate wind generally by a pressure times an area. And so the pressure may have a different distribution, and it'll have magnitudes. And then that's the way we get to a force, right, or this base shear, what we're interested in is looking at the force that would be the force at the bottom of the building, the sum of all the horizontal forces. So wind, we're going to calculate it with pressure times an area. That would be a horizontal area. Seismic, right? To do seismic, we've talked about this, you need the weight of the building. And so the weight of the building, that relates to our inertial forces that we deal with in Newton's second law. And so that V, that base shear, is going to be some fraction of the weight of the building. So the less weight you have, then the smaller the base shear, just in general. You look, see where R is. R is that reduction factor. So we'll talk about that here in just a second. You've got these two formulas for all buildings, right? This SDS times I, the importance factor. There's R, right? SDS, that's the acceleration, the spectral acceleration value at short period. And then for buildings over 60 feet, you also have to calculate then the base shear using a 1 second spectral acceleration. And so SD1 is for 1 second, and then T is the period of the building. And that's basically going to be 0.1 times the number of stories in your building. So the seismic force then would be the smaller of them. And then they get distributed across the building. And that's what comes up there on pages 12 through 15. So it's basically a triangular distribution. So we'll get more and more into that. So let's look at we'll first look at the system type, which triggers the R value. So we've got a steel concentric braced frame. So in your design projects, either you'll be deciding this. In most of the problems that I give you, you'll just be told what it is. And so then you'll have to then, if you will, fish out these values. They are in the design handbook. And so concentric would mean that it goes from corner to corner. And so you use the full diagonal, and this is from you end up with a connection. So you kind of see it right there, where you've got this concentric. Where you got the concentric connection. In comparison, eccentric would be one that does not go all the way across, but meets halfway. The reason, and it doesn't go corner to corner, the reason why you would do that is you end up then creating energy dissipation, in the beams. And so we'll talk about that a little bit more from the moment frames here in just a moment, in just a second. So you can kind of read through these. R of 6 is kind of right in the middle in terms of the R values. You'll see a range of them here. So it's kind of right in the middle. Steel is generally a very ductile material. Right. Some of the downside of this, though, is that, where you put it, obviously you have a diagonal that goes right across that bay. So it's kind of hard to have an open bay if you have a diagonal right across it. But again, from a balancing between economy and aesthetics, it's very economical. And the way that it would fail, then it would be buckling that would occur on that diagonal member. So we'll end up designing, kind of looking at the design, and we just look at that like a column. And so that's where the failure would occur if it's properly designed. And so, it protects. What we're doing here is trying to protect the columns and keep the columns upright so that everybody can, at worst, get out of the building. Here's another slightly different one. It's also concentric, but it's a steel buckling restrained brace frame. I've also heard them called unbonded braces. And so you kind of see here, so this jacket right in there is what contains the buckle brace. And so it's actually designed such that that's where the yielding is going to occur. So that all dissipates energy in the building. So it's used in areas of high seismicity. It's it says cost is close to concentric base frame because of the connection simplicity. And so that's you get yielding in the brace. So again, we're dealing with systems where we're not in some sort of performance-based design, but we're dealing with systems. All we're trying to do is remain life safe, keeping people safe in there with not a huge amount of damage, things falling on people. So steel moment frame, right, often would just be SM. I don't know why this thing, it does not, I think it's when it's connected. Anyways, so you'll see it SMF. The concept is right here, and it would be to create a system where you've got very strong columns, and all the dissipation would be occurring within the beam. And sometimes you see a notched beam right here, and so that's even trying to attract the yielding that's going to occur in the system. And so other words that you'll hear today will deal with stiffness, right, strength, which are different. I'm just going to do a quick aside here if I can get hold of my pen. I'm not doing it. So if we plotted for a material stress and strain, so the slope of that line would deal with the stiffness. Yeah, that's what I wanted. And how high it goes up here before it goes into the inelastic range, that would deal with the strength. So you'll hear those words quite a bit. So here we want a strong column and a weak beam. We would want a column or a beam where all the energy, all the yielding is going on there to keep it away from the columns. So for concrete shear walls, concrete's a more brittle material. From a ductility point of view, it's not very ductile. So from a concrete shear wall, we get a response modification of 5. Again, that's in the denominator. So you've kind of got a feel, right? We had a 6, we had an 8 right here for a steel moment frame. Again, it is, you do pay for it, nothing for free, especially fabrication with welding and inspections. Oops. Okay. Just a second here. So it's cost effective, although it's, it does also get into the weight issue of a building. Clearly, concrete, we would realize, has bigger unit weight than steel, and you can also use it in. You can mix systems and materials, but a shear wall obviously creates a very strong functional barrier. I mean, actually, typically a wall. So that would be one of the issues in terms of using that. Here would be a diagrid, which isn't something we'll end up getting into, but you see that the structure on the exterior of the building. It's quite kind of interesting design. And it's really, when we talked about shells the other day and the shape, so that's what you're seeing here. Keeping in mind that the triangle is such a stable shape. And then the last one, which we won't see very much in buildings. See if I can get one more person in here. So we'd end up with, just a second here. Okay. All right. Sorry. All right. So kind of the concrete cantilever would have a very small R value. This is also very little redundancy right here. If that column were to fail, then the entire structure would fail. So we lose quite a bit with redundancy. And you then have to pay the price by designing for a high for design forces. And this deals with, again, when we talk about the R value, that's only going to be in the seismic calculation. So you won't see those in any of your building designs. Or I guess I say I shouldn't. Be quite exciting if you did, but I wouldn't expect you to. So configuration. Right? Where do these systems need to go? Where do these frames? Where do the shear walls need to go? And what do we need to make sure occurs? And so we need to make sure that we've got adequate strength. And so this deals just with forces and stresses. So this is a stress issue. And when we get into the handbook and you find all this is actually really frustrating. The moment table, I'm just going to talk through it then. So the moment tables that are in your design handbook, like that's actually what's being incorporated in that. When you have a moment capacity, that would be a strength issue. That's a stress calculation that's masked in there. By doing that, by choosing that correctly, this is what we are guaranteeing, is that the capacity is greater than the demand. The other thing we want balanced placement. So we'll talk about that. The best way to think of it is we want it symmetric around the building plan. Vertical continuity. So we don't want to stop a system really until we get all the way to the ground. That'll deal with something called a soft story. So we'll get further into that, but we want to continue something really all the way down the building and not stop short of the ground, because at those bottom levels is where the forces have been collected and are extremely large. And then we also need stiffness continuity. We need to make sure that we have a well stiffened system and one that doesn't have stiff spots and weaker spots or softer spots. So adequate strength. We need to require enough elements, right, by count or by length. And we'll talk about how you would know that. Right, the base shear calculated for wind or seismic. The largest becomes the design force. And so that's what we're going to do today in the activity a little bit, is make sure that we've checked both directions. For the wind, seismic doesn't change in terms of direction. Preliminary strength for the elements. And so we're going to do this for a steel braced frame, right? Concentrically braced frame. In a bay, its capacity would only be 500 kips, which obviously is a big load, but the seismic loads become quite big, especially as we work to the lower levels of the building. And we'll see that on a free body diagram a little bit later. Concrete shear wall, that can be designed, and it can, the capacity would be considered 800 kips per bay, where a bay is anywhere from 20 to 30 foot long. So the bay size is important. And then the thickness of the wall needs to be a minimum of 12 inches. And then for a steel moment frame, this is a less stiff structural system, and it can actually only withstand about 100 kips per column. And so this is why you might need to add more bays, because in more columns, so more moment frames, not just one bay. And really, you need to make sure for sort of larger structures that you have a minimum of 2 bays on each face. And this also just, we want to make sure that we have some, goodness, I can't, this thing is wearing me out. Watch this. There we go. You can't beat me. We want to make sure that we have redundancy in the structure. So we don't want one, right, just one shear wall that if it were to fail, we would have no shear walls. So that's where the number, the amount, we have to have redundancy in the structure. So I'm going to do a couple of highlights here, and then I've got a sketch on the next page here. So I'm just going to let you read that for a moment, and then I'll have an example of avoiding a rotational response, which would be just building torsion. And so we'll talk about the center of mass and the center of stiffness. It's also known as the center of rigidity. And so we want those two locations to coincide with each other as best we can. So the balance of the system is kind of similar to equilibrium. And for buildings that are like L-shaped or just not square, we want to think of them as multiple pieces, and buildings that are actually maybe one building, but structurally that they would be separated. And so they would actually act independent of each other. So here would be a quick example of a plan. And so this is very, very egregious, but this would be a plan view. So this would be the floor. And let's just say we just put one big, huge shear wall because, well, we need shear walls. So we've got one there, and we've got another one right there. Maybe it just doesn't like 4 o'clock. And so the center of mass would be, roughly in the middle of the plan. Maybe it's a little bit moved towards the shear walls, which have a little bit more weight. And then the center of rigidity, though, would be all the way over here in the corner. And so when you think about this from an equilibrium point of view, right, with the, be it a statically equivalent representation of a seismic load or a wind load. So you would end up then equilibrium wise, you'd have equal and opposite forces in the horizontal direction. So there would be some force F has to be balanced over here with the stiffness with the lateral system. And those two forces have an eccentricity, and those create a torque in the building. So it's going to have the value of F times E, and that wants to create, or the building now naturally wants to twist, which is very undesirable from a structural response point of view. From an L-shaped building, this would be then designed as two separate buildings. So we would call that a seismic joint that would be designed, literally, there would be a separation. There would be, so those, it has to be big enough so that those two separate structures don't pound into each other, but they would be designed as two separate structures. Right, from a vertical continuity point of view, I'll let you just kind of read that for a second. And so here when I talk about, well, we want to take something all the way down to the ground, really when the building starts to become, bigger than 2 stories, basically bigger than residential, is where that kind of really needs to be instituted because of the forces that are present. And so that's where this becomes very important, to bring your lateral system all the way down, continuously down the building. Now, as you go down the building, it may have to get bigger. You may have to do more as you go down because of the increase in forces. So we'll look at that here in just a second. The tough part is that at those lower levels, a lot of times you would love to have something that's open, sort of unimpeded. And so that's where you get into this problem of a soft story. And generally speaking, we don't want to change structural systems because of compatibility and connectivity issues. Connecting them is very challenging. So here would be a look at a building that has a soft story down below. So it's like got shear walls, big shear wall right there, which then kind of goes down to some sort of a moment frame down there. And so you've got really large forces that are going to be present at the bottom of that shear wall. And so it's going to be very hard to transfer them into a flexible, that's a much more flexible system. So you get some singularities that would occur right there. So high force concentrations. Here would be another one where you've got a shear wall here and then a shear wall somewhere else. And so this gets into designing a drag to take the force at the bottom of that shear wall and then place it over in the top of that shear wall. So very challenging from a design point of view. Sorry. All right. Oh, goodness. This thing just gets a little sticky on me. I don't know why it does that. I'll get there. Excuse me. Sorry. Nope. There we are. All right. I think it's not going to jump. All right. Flexibility. So the concept of stiffness and flexibility work back and forth from each other. They're sort of exact opposites of each other. And so concrete shear walls are extremely stiff, 5 times more stiff than braced frames. And then I go ahead and just say it exactly opposite. Instead of talking about how stiff concrete is, we would say that the steel brace frame is more flexible than concrete. So that's why it's challenging to have both of those systems trying to work together. You can put them in different directions in a building. You could have shear walls in one direction, and then in a totally different direction, you maybe have shear walls here, and then maybe moment frame here and here. That would be doable because they're working in perpendicular directions. So steel brace frame is 5 times more stiff than a moment frame. So a moment frame is very, very flexible. And so that's why there was, less force that could be applied to each of the columns in it. So we generally want stiffer elements at the bottom. We don't want stiff elements on top of flexible elements, but you can put flexible on top of more stiff elements. And so then I also just kind of hit back with the center of rigidity. I wish this were funny. It's not. All right. Let's see if I can. All right. So here we'd be back to a picture on the left here. We've got a shear wall on one side and a moment frame, a steel moment frame on the other side. So we have a very big stiffness incompatibility. The shear wall is much more stiff than the moment frame. So there's the center of rigidity, right? The stiffness center. And then there would be the center of mass. So this creates the torsional response. Now you could, then one way to get in line is to have a smaller shear wall. So something that would have less stiffness to it. So it has less length is another way that a shear wall gets its strength, its stiffness. But when you do that, then the design of that shear wall becomes more important or more critical. So just kind of keep that in mind as you look to put a lateral system in. And then the very last one here. This is wearing me out. And now lines are just showing up that I haven't drawn. Outstanding. So here would be a picture of, and this is just on one line here. So I've got a shear wall and moment frames together. And so this is not really, not very smart, because the load is going to be attracted to the more stiff element. So the shear wall is going to be doing all the work. The moment frames really aren't going to be contributing that much. So that's one way that you'll think about when you lay out your your lateral system. All right, design elements, and then this will kind of get us done here. So steel brace frame, concrete shear wall, steel moment frame. We're going to focus really on the first two here from an element design point of view. And what you're going to do is trying to get to the, checking that the capacity exceeds the demand. So, all right, steel brace frame. So horizontal shear force at all levels, right, would show up. This is from seismic here, is how I've grouped it. So the triangular load, right, largest at the top. As you go down, the forces on the levels, at the floor levels, decrease. But if you were to take a cut here, right, and do a free body diagram, then all of those forces have to be resisted by 1, 2, 3, 4, by those columns right there. So just think about it from a free body diagram perspective. So this is one where, right, as we go down the building, I actually make more, right? I get more capacity down here because of the higher forces, the higher stress demand. You can do more than 500 kips on a bay, but then you would need to validate it with your design. So that's why down here I would have 2 bays, not just, 1, 2 working in this direction. If the aspect ratio is greater than 3, then you have to check column size, and those column size would be down here, where the overturning moment would be very large. So as this becomes, this would be what we would call a slender, sort of a slender building here, where the height is much, much bigger. And 3 would be the number, but as it exceeds that, then your H over L, this thing becomes something very slender. And so not only do you have a base shear down below, but you then have a very large bending moment that would show up. So we use then a beam analogy to kind of get us right in terms of the aspect ratio. So that's why, as I went down here, then that's why I added more frames down there, help with the aspect ratio. From a shear wall, you get a minimum of 12 inches. Right, from a capacity point of view, the capacity is 250 psi or 0.25 ksi. So we're going to do a calculation here in just a moment, and that needs to be greater than the demand, right? Or the demand needs to be less than the capacity. And also, if the aspect ratio, this is for a shear wall, right? This is for a shear wall. So if that aspect ratio, again, is greater than 3, right? So it's that configuration. Then we need to check this as if it were, because really what it is a beam. It's a bending beam. So we've got loads that are coming in this direction. And so if we think of it like this, I can't believe I can't draw. So that's what it looks like if we were to turn it. And so you've got some loads. Those are the seismic loads or the wind loads. And so it really becomes just like you would on any beam design, right? You have to have a moment capacity, so that BH squared over 24 comes back in. And so we've seen that before. It's just that when we do it here, right, it's going to be B is the wall thickness, and then the wall length is going to be H, the length of the shear wall. So let me give you one example, and then we'll be done here. And so here would be a 2-story shear wall structure. We've got some windows that are present. So this is 30 high and 30 long, so it's got good aspect ratio. And the openings are not huge, so we can treat it as if it's one, sort of think of it as if it's one shear wall. And so you see the seismic forces, right? The 500, then it decreases to 250. So in total, we've got 750 base shear. And what we're going to do then is check the demand on the structure. And so this shear wall, we're going to think of it like a beam that's sticking up. And the place that we're going to check the shear is going to be through the window, because that window is a void. And so the cross-sectional area, if you think of that, I'm going to try and draw this. And I'm sure I won't be able to, because it's just not meant to be. You know what? Maybe I will. So, although this is hard to see, this is 12 inches. I didn't draw that very well. That's the thickness of the wall. So what this is a view right down. I'm going to look straight down. And so here is the window. That's the void, right? So when I say the area and we do the shear calculation, we're going to do V over A, and A is, I'm even going to do a different color. I would jokingly say no extra charge for that extra color. And then that would be the area. That's the cross-sectional area of the beam where the window is present, making a void. So that's why I don't use 30, but I go 30 minus 8, giving me 22. And so it works. I've got an adequate design that the calculated shear stress is less than the capacity of 0.25. Don't need to do bending. Don't need to do bending because we have a 1-to-1 ratio on that. So if the building were huge, like 200 feet, then we would need to check the bending down there and check those forces. So, all right. So with that, I'm going to put this in front of you here. So what you're going to do, we're going to take, I'll do this, take about 5 minutes. We'll take a break. It's 4:55, so we'll come back at 5. And so what I've done is given you a building plan. You got a 4-story building. And I actually asked you for 4 answers, but I've given you 2 of them. And so that's meant to help you be able to check. You should be able to get those, reproduce those. And then you can do the other direction. So you've got some seismic and some wind to deal with. And then you're also going to do a much taller building, a 40-story building. And so why don't we do that? I will, we'll take about a 5-minute break. I'm going to put you in your groups that you were for project 1. And so the hope is that we can fill in the boxes that we need. You've got everything up here. All the values are there for you. And then we'll see if then you would have a little bit of time. Stop sharing, get back to this. I got it downloaded. And so, is this the posted on Canvas? I believe it is, but let me check. So, and yes, actually also homework 1 answers, they are on Canvas. Just scroll down. If you just scroll down on our main page, I made a new module down there. So, if you want to go, you feel free to take a break. I will show you where that is, Shiva. Yeah, it would be right there, right down at the bottom there. And here would be the class 6. Let's see if somebody said I don't have the right one there. I think what I'll do is just email it to everybody. How about that?